Hi, the section 8.4, the diagnostics. So there are two main objectives of regression diagnosis. So one is to detect unusual observations, such as outliers and influential points. So we would like to have the estimation results based on a large sample size. But if a few observations affect the estimation results significantly, then that means the estimation results are actually based on a small number of observations. So we would like to avoid that situation. And the second objective is the checking assumptions of the model. So sometimes predictors are missing. So if the true model is y on x1 and x2, but we only have x1 in the model, that is not good. We would like to detect that. Also, if the true model is y is on x1 square, then the model y on x1 isn't the best. So we would like to detect that relationship also. Also, errors should be IID in basic statistical models, so that we would like to check that assumption. And some of the concepts in 8.4 are used for both objectives, and some are used for only one of these objectives. So first, residuals. So residuals can be used for both objectives. So residuals are used to detect outliers. So that is for sure. So large residuals means the outliers. And also the residuals can check the model specifications through residual plots. For example, if residual plots are like this figure, then you can see the x and y has nonlinear relationship. So we have specific pattern in residual plot. So that violates the assumption of IID assumption of the error terms. And the residual plots, residual analysis are not feasible for some cases, especially binary responses, and also responses with only a few possible values. For example, the count data with only 1, 0, 1, 2, and the most of the time, the values are 0 or 1. It's similar to binary response data. So since one observation has a very small amount of information, it's not meaningful to see the residual plots. But it's useful for other cases. And we discussed the several versions of residuals in this video. So first one is the Pearson residual. So Pearson residual is y minus mu hat. So this is usual residual, but the divided by square root of v of mu hat. So this is the variance depending on mu hat. So typical case is the binary response, or maybe the binomial response. We have y and the expectation of y exists. And actually, suppose the expectation of y is p, then variance of y is proportional to p times 1 minus p. So Pearson residual accounts for this fact. Second one is deviance residuals. So this is negative 2 times log likelihood. In case of the Gaussian distribution, e to the power, the negative r square over 2 is the density function, the likelihood function. And if we ignore the variance term, and then negative 2 times log likelihood. So that becomes just r square. And the deviance residual is just the reproduce the sign for this r, and that we would define the positive or negative r as the deviance residual. So to be exact, at first that we think about the deviance for the ith observation, so di. Then we regard this as the square of something. So suppose the r square is equal to d. Then we think about the sign of y minus mu hat. So whether the estimate is too large or too small compared to y. Then we multiply the square root of d. So in this way, we can define the deviance residual in a similar way as the Pearson residual or usual residual. So here, in both formula, the index I is dropped, but to be exact, we have to have all index yi, mu I, hat I, and so on. Just I is suppressed. And the third one is response residuals or just residuals. That is y minus mu hat. So in the binomial or binary regression, maybe, okay, so y is either 0 or 1 if binary case, and mu hat is probability of y is equal to 1. So R is residual. And working residuals, RW, are residual from the iterative reweighted the least square fit. So that is residuals in the scale of eta. So eta is equal to link function g of mu. So in general, if we think about everything in the scale of eta, it's easier to see. Because the y and the mu hat are basically, the mu hat is a product of the highly nonlinear the function of x and beta. But these residuals, the working residuals, are not used in this section. And for linear model, these four residuals are all the same. So we don't have any difference, but the generalized linear model based on the difference in assumption. So these residuals are slightly different. So next slides explain how to calculate those residuals. So the some example is the GLM1. So GLM1 is basically the binomial model with this x and y. So remember that this is the pesticide data. So x is the amount of pesticide and y is the number of survival, maybe the number of deaths. And yeah, y is given as a proportion such as 2/30 over 8 or 8/30. So at first, the Pearson residual. So these are the residuals. And this is Deviance residual. Even though the definitions are totally different, actually these are similar numbers. So you can specify the Pearson or Deviance in residual function to get these numbers. And the third one is usual response residual. So this is maybe easier to interpret. So this means the 2.3% underestimate for this proportion 2/30. So estimated proportion is the 2.3% higher. Maybe so 2.3% overestimate, we should say. So y minus mu hat is equal to the negative 2.3%. So it's estimated as, okay, so this is 6.7%. So it's estimated as 9%. So y is 6.7% and the mu is equal to 9.0%. That is what happened here. And it can be obtained directly taking the difference between sample proportion is here, and minus fitted value. And the working residual can be obtained by this way. Maybe you can compare the Pearson residual with the usual residual, response residual. Then you can see that maybe these two numbers are relatively larger in terms of absolute value compared to these ones. So here, actually, this is smaller than this, and this is slightly larger than this, but here, the difference is larger. So this is because the first observation and the fifth observation, fitted values are closer to 0 or 1. So that means the variance of y is proportional to p times 1 minus p. So this variance is small. So we divide the residual by the standard deviation of y for a Pearson residual. So that means the first and the fifth residual gets relatively larger in absolute value. Yeah, so these are how to create the residuals in our language.